Okay, we're going to find volumes now, and the first kind we're going to look at is some solid where if we sliced it, all the cross sections are going to look the same. Now, the idea here is we've got this solid that's sitting on the XY plane. If we took one slice of it here, if I can find the volume of that one slice, then all I need to do is find the volume of all the slices starting from the x equal a to the x equal b down here. And so I'm going to integrate to get the sum of all of these, the sum of all of those volumes. So find the volume of the k slice and then integrate it from x equal a to x equal b. And of course, part of the volume there is that delta x, which is already in that right there. So you're going to be looking at the integral of the area of that one k slice times the width of it, which gives you the volume. Okay, so our goal here is to figure out the area of one slice of it and then use the integral to accumulate to add all those volumes together. Okay, so the slicing method. Suppose you have a solid that extends from x equal a to x equal b, and the cross section of the solid is perpendicular to the x-axis. If a is an integrable function, on the interval from a to b, the volume of the solid will be the integral of the a of x dx. Okay, so the idea here is just we're trying to find this volume here of this solid. We're going to do it by splitting it into smaller little pieces here, the volumes of these one little slices, and then as you let the number of slices increase here to here, you're getting closer and closer to what the actual volume of that solid will be. So you're summing up all of the volumes of the slices, then you're going to take the limit as n goes to infinity, and that translates to that definite integral. Okay, so now we have a solid that has a base that's bound by these curves, y equal x squared and y equal 2 minus x squared in the xy plane. Cross sections, they're telling us how to get these cross sections. Cross sections through the solid perpendicular to the x-axis are going to be semicircular discs. Okay? So we're slicing it perpendicular to the x-axis, so a slice down this way is going to give us this disc. And they tell us it's a semicircle. I want the volume of the whole solid. Okay, so now that's one cross section here. And notice what the boundaries of this thing are. Our boundaries are the curves y equal to x squared and y equal to 2 minus x squared. So that's telling us where the bottom, what the bottom of that solid looks like. So let me draw those a little bit so I can see it a little better here. And 2 minus x squared. Okay, so this is the base of the solid. And I'm told if I slice it perpendicular to the x-axis, so slicing it this way, this will be the bottom, that one line that would go across the bottom of that solid. Okay, and I know I have a semicircular disc here. So this will be the actual bottom of my slice. If it's a semicircle, the thing's coming up over that line there, what I need to do to figure out the area of that one semicircle, I need the area of the semicircle, and I know that that's just going to be 1/2 of pi r squared, because the area of a circle is pi r squared. So now my integral to get the volume is going to be the integral of the area of a semicircle. Okay, and then I'm going to need to know what those x values that it's between. Well, the x values that region is between are these, which are just going to be where those two curves intersect. So if I have x squared equal to 2 minus x squared, I get 2x squared equal to 2, so x squared is 1. So that's x equal 1 and negative 1. Okay, so we go from negative 1 to 1. Now the area of the semicircle. All I need to figure out what the radius is. Okay, so now I need to find the area of that semicircle, which is based on this, which is the radius. This will be the diameter of the actual semicircle. So this right here is this bottom that will be the diameter of this semicircle. So if you look at this length, then half of that's going to be the radius. So to figure out what this distance is, I can take this function's value minus this function's value. Well, this top one is y equal to 2 minus x squared, and the lower one is y equal to x squared. So the radius is equal to half of 2 minus x squared, the upper bound, minus the lower boundary, which is x squared. So the radius then will just be 1 minus x squared. Okay, so when we set this integral up, I just need to put the area of that one slice, and then I'll have the dx, and then I'm going from -1 to 1 to add up all those slices, those semicircular discs. So the area of that one semicircle is going to be 1/2 pi times the radius squared, because it's a semicircle, and the radius we know is 1 minus x squared. So 1/2 pi r squared, and then dx. And this will give us what the volume of this solid will be. And you can go ahead and finish this. I'd pull out the 1/2 pi out in front. I would need to square this out. I can't use a u substitution since I don't have an x outside of the parentheses. So I would have 1 minus 2x squared plus x to the 4th, and that's going from -1 to 1 still. So I'm going to have, just use the power rule. So you're going to have x minus 2x cubed over 3 plus x to the 5th over 5. And all that's evaluated from -1 to 1. And then I have the 1/2 pi out in front of this entire thing. Let's see what that answer should be. Should come out to be 8 pi over 15. Okay, so that's just evaluating that out.